Okay, so in this lecture we will be talking about class equations. Okay, class equations. It's also called simply accounting formula. Accounting formula for groups. Specifically, it's called the second counting formula. The first one, I guess, it's called this one is called the counting formula. First counting formula, I guess. The order of hk is order of h times order of k times order of h intersection divided by order of h intersection k. I guess this one is called the first counting formula. Whatever, we are not concerned about that. But this class equation is essentially very required to analyze certain very important properties for P groups. And the concepts of class equations are, entangled between studying centers and centralizers. Okay. So before watching this lecture, please go and revise the concepts on centers and centralizers. At least go and revisit the definitions of them. So let's start. Um, okay, yeah, I think we are good to start. So suppose, okay, let's start with a simple definition. Let G be a group. Let G be a group, and let us choose two elements from G. Then we say that A is a conjugate uh, of B in G if there exists some element small g in capital G such that A can be written as G inverse BG. Clear? Okay. Clear? Now, yeah, so that's the precise definition. As a simple observations which directly come out from this definition is that number one is that if we can write A as G inverse BG for some G in capital G, then we can also write B as G inverse by specific left and right multiplications of G. So G and G inverse specifically, whatever. But then observe that this implies that B is also a conjugate of A. B is also a conjugate of A because we can precisely write G as G inverse whole inverse and you have G inverse here, right? So in a way, saying A is conjugate of B or B is conjugate of A can be restricted to just saying that A and B are conjugates, right? Because if A is a conjugate of B, then B also comes out to be a conjugate of A. So we can simply say that A and B are conjugates. Okay. Okay, this is a very obvious observation. The second observation is that if I choose an element A, then I can write A as E inverse A E or whatever you want to write, 1 inverse A 1, right? Whereas I can express A as a conjugate of itself. So every element is conjugate of itself, right? The third observation, which I guess you people should now or already have guessed, is that if I can write A to be G inverse B G, and I can write B to be, say I can write A to be G1 inverse B G1, and I can write B to be say G2 inverse B G2, sorry C G2, then I can write A simply as G1 inverse G2 inverse C G2 G2 inverse, right? Yeah, G2 and G1 here. So the first element can be written as G2 G1 whole inverse C G2 G1. Now G1 and G2 both come from the group capital G, hence by closure G2 G1 is also an element from capital G. So this readily implies that if A is a conjugate of B and B is a conjugate of C, then A is a conjugate of C as well. right? So what should be the immediate lemma I should state at this moment is that if we define this, let's say, if we define this to be a relation on G such that A is related to B if and only if A and B are conjugates. A and B are, or I should now be writing it like A is a conjugate of B. Let's say A is a conjugate of B. A is a conjugate of B. Then by the above observations, uh, this relation is an equivalence relation, right? This relation is an equivalence relation, clearly, right? Yeah. So therefore, right, when we have already defined an equivalence relation, then again the immediate next result should be, one second, guys. Okay, yeah. So this is an equivalence relation, right? Okay. So therefore we can state an equivalence class. That should be the immediate next step. So so what should be the equivalence class of A under this relation? Let's say. So these are the collection of all the elements X in G such that X is related to A, or I can say that X is a conjugate of A, or I can say that A is a conjugate of X, whatever I can say. Or simply I can say that X is contained in G. Let me say it like this, that A is a conjugate of X for now. Okay. But A is a conjugate of X. This means that there exists element G in capital G such that A can be written as, rather, let me say X can be written as G inverse A G, right? Now, since we are having a set notation in this case, so simply I can write this as the collection of all the conjugates of A such that G is in capital G. And obviously, this set will contain all the distinct conjugates of the element A, right? This is what we denote as, say, CA, and it's called the conjugacy class of A. It's called the conjugacy class of. We further denote, so these are just me setting notations. Okay, we further denote the number of elements in C of A as CA, okay, or rather small ca, whatever you can, yeah, so CA, let's say. Okay, now we know that equivalence classes partitions the group G, hence also G should be a disjoint union of all these conjugacy classes of A, where A varies over the elements in G. But then I can express the order of G as summation of all the small CAs, right? As A varies over G. Clear? And appropriately that this is, this is more appropriate when I am talking about a finite group, right? Because talking about the order of a group and expressing it as a sum of certain elements is more appropriate when we discuss about finite group. So yeah, you can think about G to be a finite group, but rather we have not mentioned it anywhere, so it's sort of an arbitrary definition as well. Clear? Okay. Now, okay, let me give a hint to centralizers. Recall how we defined centralizers for an arbitrary subset A of capital G. It was defined to be the collection of elements small g in capital G such that G capital A is equals to A capital G. Sorry, this is the definition of a normalizer. Sorry. Yeah, so G small a is equals to A small g for all small a in capital A, right? These two definitions are obviously not exact. Writing G capital A is equals to A capital G implies that GA is equals to A1G, where A and A1 both are elements from capital A, but they may not be same. while G A equals to AG, we are restricting A and A1 to be same. So normalizer is sort of a uh, higher concept than centralizers in a way. Right? Okay. So precisely now, if I restrict A to a singleton set, suppose I rate a singleton set, then the centralizer of capital A is usually denoted as simply the centralizer of the element small a. And it precisely consists of all those elements small g in capital G which commute with A. That as simple as that. Okay. So now we come to a very important result, or you can also think of it as a very important observation, which I will be stating as a theorem, which says that if G is a finite group, if G is a finite group, then the number of distinct conjugates of A in G equals to the order of G upon the order of the the order of G upon the order of the centralizer of A. Okay, clear? So the number of distinct conjugates of A equals the order of G upon the order of the order of the centralizer of A, right? Or I can also say it like this, that I could have also expressed this as the index of the centralizer of A in G. Okay, which typically means so these are just observations, so let me just change the color. So I actually mean to say that the number of distinct conjugates of A is equivalent to calculating the number of distinct left cosets or right cosets. Let me be precise to left cosets or right cosets, whatever. The number of distinct left cosets. Let me do it right cosets. Ordinarily, we always use left cosets. Number of distinct right cosets of the centralizer of A in G. That's indeed what we will be proving now. Okay, so proof. Okay, so what we essentially do is, first thing which we do, we consider two elements which represent the same coset of the centralizer of A in G, and we show that both of these elements, I mean the conjugate of A with respect to both of these elements, are identical. Okay, and then if we consider two different representatives, I mean, sorry, if I consider two elements from distinct cosets of the centralizer of A in G, then I'll show that the conjugate of A with respect to these two elements are different. Okay, that will essentially give the required one-one correspondence between the number of distinct cosets of centralizer of A in G and the number of distinct conjugates of it. Okay, so let X and Y be in G. Let X Y in G be in the same coset of the centralizer of A. Okay, yeah. So we did that. That's a good point to start. Okay, 1 second. Okay, clear. Okay. Yeah. So we consider X and Y to be in the same coset of the centralizer of A in G. So that implies we can write Y as Nx such that N is in the centralizer of A. Correct. I can do it, right? Being elements of a coset. But since N is in the centralizer of A in G, then I can write Na is equals to An. Okay, this is precise. Now, if y, if I calculate y inverse, then it will come out to be x inverse n inverse. But then this implies that y inverse A is equals to x inverse n inverse A, right? But this implies y inverse A y is equals to x inverse n inverse A n x, right? Uh, so I can probably associate this part, but observe that n inverse A n inverse A n is nothing but A, right? Therefore, this is exactly equal to x inverse Ax, right? So if I choose two elements from the same coset of the centralizer of A in G, then I'm getting same conjugates, identical conjugates. What if I choose two different elements? I mean, two different elements in the sense two elements from different cosets. Okay. So let x and y be elements from different cosets of the centralizer of A in G. Okay. Suppose they give same conjugate. Okay, so y inverse a y and here x inverse a x. Okay, I'll probably reach some point of contradiction. Okay. So this implies that y inverse, yeah, I can probably write it like this. Okay, so I have y inverse a y is equals to x inverse a x. I can probably write it like, if I multiply y on both sides, I'll get yx inverse ax is equals to ay. So I'll get yx inverse a xy inverse is equals to a. But then yx inverse, I can probably, so observe that this is yx inverse a is equals to a. Yeah, this is yx inverse only, right? Yeah, correct. Correct. Got it? Okay, I could have done this by just putting x here. Sorry. Whatever this implies that yx inverse is contained in the centralizer of A. But observe that this implies y and x come from the same coset. Come from the same coset, right? Which is a contradiction because our assumption was they come from different cosets, which is a contradiction, right? Therefore, we have established a one-one correspondence between the number of distinct conjugates of a given element A in G and the index of the centralizer of A in G. Okay. Now, this immediately gives us what we wanted to introduce in this lecture is what we call the class equation. Because observe, since order of G is the summation over the number of distinct conjugates of A in G, ranging over A in G, elements A in G. So I can write this as summation over A in G, the order of G upon the order of the centralizer of A in G, right? And this is what we call the class equation. This is what we call the class equation. Okay. Now, it should be an easy exercise if you have already revised the concepts of centralizers to justify or rather to check the class equation for abelian groups, at least finite abelian groups. Class equation for finite abelian groups. Finite abelian groups. Just keep in mind the fact that if you are talking about an abelian group, then every element in the group will commute with A. So the centralizer of A should be the whole group. Okay. So check the representation of class equation for finite abelian groups. Okay. So yeah, I guess there's nothing more to discuss. But now we come to the important concepts which I want to discuss today. The first thing is an easy lemma. I don't want to prove it because this is very easy to prove by anyone who just at least just know the definition of centralizers and centers. Okay, it says that an element is in the centralizer of an element is in the center of G if and only if the centralizer of that element is equal to G. Furthermore, if G is finite, if G is finite, then an element is in the center of G if and only if the order of the centralizer of A equals the order of G. So proving the first statement immediately proves the second statement as well, but the first statement is also very easy to prove. It just comes from the fact that if you choose an element out of the center of G, then every element in G will commute with that very element, right? So G must be contained in the centralizer of A in G, but that immediately means that G must be equal to the centralizer of A in G. Other way around is also pretty trivial. Okay, there's nothing too complicated to prove here. What we want to prove is the following theorem, that if you consider a P group, let the order of G be P to the power n, where P is a prime, and n is some natural number, then the center of the group is non-trivial. That is, its order is always greater than 1. Order of ZG is always greater than 1. Okay. Or at least it's not equal to identity. You can just represent it any way you want. Okay. So how do we prove this out? Okay. So proof. Okay. Firstly, observe that if I choose an element from the center of G, then we know that this element is in the center of G if and only if the centralizer of A is equal to G. Right? This is pretty obvious. I guess, yeah, I should write it first. Okay, that's not a problem. Now, what I want to say is that for all A in G, the centralizer is an obvious subgroup of G. This implies that the order of the centralizer, the order of the centralizer of A must divide the order of G. This follows from Lagrange's theorem. But order of G is P to the power n. So this implies the order of the centralizer of A must be some power of P as well, such that the exponent is less than n, less than or equal to n, with Na less than or equal to n. Clear? But suppose this is statement 1. But from 1, it's obvious that A is in the center of G if and only if the order of the centralizer of A, which we have represented as P to the power n indexed with A, if and only if Na equals to n. Right? This immediately follows from 1. Clear? Clear? Now, observe this element. Order of G upon order of the centralizer of A, where A ranges over the elements in G. Now, when we are talking about elements running through, when we are talking about this element A, which ranges over all the elements in G, it will obviously also run over all the elements in the center. So, whenever this element A, it appears to be an element in the center, then the order of the centralizer of A, it equals the order of G. So essentially, the summand becomes 1. If the summand becomes 1, we know that summing over 1 up to some certain number of elements immediately gives you that number of elements. So we will end up with an element in G when we are doing this summation. We will end up with an element in the center. The number of times we will be ending up with an element in the center, we will get 1 every time, right? Therefore, if order of Zg is equals to Z, then observe that this summation will give us Z plus the summation, the exact summation where the power of where Na is less than n. Okay, what I'm trying to say is that what I just said, specifically what I mean is that whenever A becomes an element in the center, Na becomes n, so the summand becomes 1. And how many times will the summand becomes 1? It will become 1 exactly the number of times A comes out to be an element of the center. there are z number of elements in the center. Therefore, A can become an element of the center z number of times. So we will get z once, right? Then this summation A in G, order of G over order of centralizer of A, this will become, so this will give, one z time. So we have z plus, and the rest of the summation we can restrict it to say that this summation occurs over all those elements A such that the exponent Na is less than n, because the possibility of Na to be equal to n is omitted by bringing out all the elements in the center. I hope this part works. Okay, clear? Therefore, we can modify the class equation. This is also one sort of representing the class equation as well. We specifically write the elements of the center because we know, because from this lemma we know that an element is in the center if and only if its centralizer equals G. So we can just bring out the elements in the center separately and then write the summation where the element A ranges over all the elements in G which is not in the center, or the complement of the center of G in G. Okay. You might also get this representation in most of the books. Okay. Whatever. Therefore, what I mean to say, therefore by class equation, the order of G is equals to Z plus summation over Na less than n. Now we can write it like this: P to the power n over P to the power n. Okay. Now the left hand side is P to the power n. We know it. Since P divides the LHS, P will also divide the RHS. Moreover, since Na is less than n, therefore the factor of P remains in the numerator. This implies P will divide P to the power n over P to the power Na. This means it also divides the summation over Na less than n, P to the power n over P to the power Na. Right? So this means P will divide P to the power n minus summation P to the power n upon P to the power Na, where Na is less than n. But this would immediately mean that P divides Z, right? But we already know, but Z is not equals to 1, right? As sorry, Z is non-zero. I mean Z, the center is non-empty. Sorry, but the center is non-empty, as the identity element is obviously in the center. This implies the order of, Z is greater than 0. Now if for P to divide Z, since P divides Z, Z obviously cannot be 1, it has to be greater than 1. Z needs to be greater than. And that was exactly what we wanted to do. Okay, clear? Therefore for a P group, the center is non-trivial. Clear? Now if I restrict this P group to a group of order P square, then we can say something more. Okay. So that will be our next theorem. Or I can simply say it to be a corollary, because we will be using this fact which we just proved. So I can say this as a corollary. If order of G is P squared, then G is abelian. Then G is abelian. Obviously where P is a prime. Where P is a prime. So we previously had this observation that if I talk about a group of order P where P is a prime, then it's not only abelian, it's cyclic as well. Right? In this case, we can talk about a P group of order P squared to be abelian. Okay. So let's check the proof of it. The proof of it is also quite simple, because since G is a P group, which we already know, then ZG is non-trivial, right? ZG is non-trivial. This implies that the order of ZG can either be P or P squared, right? Because by Lagrange's theorem, the order of ZG must divide G. G is of order P squared. The only factors of P square are 1, P and P square. ZG is non-trivial. Its order cannot be 1. So the only possibilities for the order of ZG is P or P square. Now, the obvious possibility is that if ZG, if order of ZG is equals to P squared, we are done, right? Because ZG is a subgroup of G. If G has order P squared, and if also the center of G has order P squared, then ZG must be equal to G, which implies that G is abelian. So that's quite the trivial case, right? So let the order of ZG be equals to P. Okay, clear? Okay. Now let us choose an element from G such that it is not in the center. Okay. So this immediately implies that the centralizer of that element is not equal to G. Therefore, now ZG is obviously contained in the centralizer of A, and the centralizer of A is properly contained in G because the element A is in G, and we have seen that the centralizer cannot equal G. But observe that also A is in the centralizer of A because A will obviously commute with itself, right? This implies the center of G is also properly contained in the center of G is also properly contained in the centralizer of A, right? But the center of G already has order P. This implies that the order of the centralizer of A must be greater than P. But it should also divide the order of G, right? Because it's a subgroup of G. This implies that the order of the centralizer of A must be equals to P squared. But that's exactly the order of G, right? But we had concluded the fact that they are non-equal. Therefore, it's a contradiction. Or you can also continue this fact by stating that if the centralizer of A is equals to P square, that is if the centralizer of A equal G, then immediately we have the fact that A must be an element of the center. But that's again a contradiction, so we can approach it by the base. Okay, I guess it's clear. Okay, because we had previously seen the fact that the centralizer of A is equal to G if and only if the element A is contained in center of G. Okay, so this it's an obvious proof. Okay, clear. Now we come to the most important conclusion, or rather one of the most important conclusions of this lecture, which is the generalized Cauchy theorem. The generalized Cauchy theorem. I guess in some previous lecture, I had given the proof of the Cauchy theorem for finite abelian proofs. I'll though repeat it in this lecture as well, but I don't exactly remember whether I had covered it or not. Whatever. The generalized Cauchy theorem. What does it say? It says that if P is a prime, such that P divides the order of a group G, then G surely has an element of order P. Then G has an element of order P. Okay. How do we prove this? So the method we will be using is the strong principle of induction. What we will do is that we will assume that this hypothesis holds, or I should say the statement holds, for all groups of order less than the order of G, and then we prove it for order of G. Now, obviously, we can consider this hypothesis because uh, the order. I mean, this statement trivially holds true for order of G being 2. It also, vacuously holds for order of G being 1, right? Now, observe that if I consider this statement that consider this hypothesis that this statement holds for all groups of order less than G. Suppose P divides the order of H where H is a subgroup of G, say a proper subgroup of G. So if P divides the order of a proper subgroup of G, this subgroup will have order less than G. Therefore, the hypothesis holds for this subgroup. By induction hypothesis, there exists some X in H such that order of X is equals to P. Because we have assumed that this statement holds for every group which has order less than G. So if I get a subgroup of G such that its P divides its order, then by induction hypothesis that subgroup must contain an element of order. But if X is in H such that order of X is P, this obviously implies that X is in G such that order of X is P, because H is contained in G. But therefore it's trivial. Therefore it's a trivial case. Right. So for the proof to be more generalized, we need to assume that. Therefore, we assume that P does not divide. P does not divide any proper subgroup of G. Okay, clear? Now let A be an element outside the center. This would imply that the centralizer of A is not equal to G. Okay. Then this would imply that the centralizer of A is a proper subgroup of G. Then this means that P does not divide the centralizer of order of the centralizer. Clear? Now, by class equation, what do we have? By class equation, we have that the order of G is same as the order of its center plus summation over the order of G upon the order of the centralizer of A in G. The summation ranges over all the elements outside center in G. Okay. Now, P divides order of G. That's by given hypothesis. We need to show that there does not exist. I mean, there exists an element of order P in G. Also, since the order of the centralizer of A in G does not divide the order of G, since P does not divide the order of the centralizer, so this immediately implies that the factor of P remains in the order of G, because since P divides order of G is some multiple of P. Since P does not divide the order of the centralizer, the factor of P is still there in order of G after the division happens of order of G and order of the centralizer of A in G. This immediately means that P must divide the order of G. Or so in every summand this happens, right? In every summand this happens. Clear? So in other way, P divides the summation over order of G. I should use order of G upon order of the centralizer of A in G. I'm very sorry. Okay, this is what I wanted to say. So this means it happens for every summand. So you have this immediately, right? But then this implies that P divides the order of the center of G as well. But if P divides the order of center of G and center of G is a subgroup of G, this immediately means that by our assumption the center of G must be equal to G. But if the center of G is equal to G, then G is abelian. So if G is abelian, then it follows from the Cauchy theorem of finite abelian groups. Okay. Should I give a proof for the Cauchy theorem of finite abelian groups? Yeah, that's the problem. I don't remember whether I had, whether I had given the proof of it somewhere or not. I exactly don't remember it. Okay, let me give a proof of it. The proof is very simple. The proof for finite abelian groups is very simple. It's nothing. There's nothing very complicated there. Okay. Okay. So let's give a proof of it. One sec. One second. Where did my pen go? Yeah, I got it. So, Cauchy theorem for finite abelian groups. Okay. So what I'm trying to show is that if G is a finite abelian group, I'm not writing it anymore. If G is a finite abelian group and P is a prime such that P divides its order, then there exists an element of order P in G. Okay. So again, for the proof of this, we will use the strong principle of induction. That is, we will assume that this statement holds for every group of order less than G, and then we will show it for G. Okay. Um, See, first thing first, if P is a prime such that P divides the order of G, then there exists an element in G of prime order. I'm not saying, see, we want to show that there exists an element in G of order P, not any arbitrary prime order. But the obvious observation which comes out is that if we have a prime which divides the order of a finite abelian group G, then there surely exists an element in G which is of prime order. Why is it so? Why is it so? This statement actually does not depend on P dividing G. That this statement is actually a bit arbitrary. The reason is, suppose X is in G, then such that, let's say, order of X is M. But then then M can be written as, say, NQ, where Q is a prime. This comes from the factorization of integers. But then observe that if order of X is M and M is equals to N times Q, then order of X to the power N is Q. Right? This comes from the properties of order of an element. Right? Observe that, just recall the fact that order of X to the power A is given as order of X upon the GCD of order of X and A. Okay, this comes out from here. Therefore, surely there exists an element of prime order. If this element has order equals to P, then we are done, right? So let me just write it like this. There exists an element in G, say X, such that order of X is equals to Q, where Q is a prime. Where Q is a prime. Therefore, if Q equals P, we are done. We are done. So let Q be not equal to P. Okay, let Q be not equal to P. Now what we do is that we consider the cyclic subgroup generated by X. Consider the cyclic subgroup generated by X, and then we immediately consider. So what we try to do is that we need to reach a group which has order less than G, such that P divides the order of that group, because we have assumed by our induction hypothesis that if I consider a group which has order less than G, such that P divides the order of that group, then that group has an element of order P. So if I try to bring our observations down to a group which has order less than G and P divides the order of that group, then we can apply the induction hypothesis to it. And what should be our obvious work to get such a group is just to quotient out, right? So consider G bar to be the quotient of G modulo this cyclic group generated by X. Why is it useful? Because P does not divide the order of this cyclic group G. Because the order of this cyclic group the order of this cyclic group generated by X it is having order q because the order of x is q, and p is not equal to q. So p immediately does not divide the order of the cyclic group generated by x. This means p divides the order of g upon the cyclic group generated by x. The other way down, this means that p is dividing the order of g bar. But again, this cyclic group is clearly non-trivial cyclic group, right? It's not, because x is a non-identity element. We have assumed its power to be I mean its order to be a prime, right? So the order of g bar is surely less than the order of g, right? This immediately comes from the Lagrange's theorem. There's nothing too complicated here. Therefore, by induction hypothesis, g bar has an element of order p, and say the element is y times the cyclic group generated by x. Okay. Therefore, y the cyclic group the element y times the cyclic group generated by x to the power p should be identity, but this implies y to the power p times this is identity. But this immediately means that y to the power p is in the cyclic group generated by x, right? Right. So what should be the obvious observation out from here? Now observe that if y to the power p is equals to e, okay, if y to the power p is equals to e, then we are done, right? Then we are done, right? Because if y to the power p is in x, so it's obvious that if y to the power p is equals to a, then we are done. Y is the element we want to talk about. Else, if order of y to the power p is equals to q, then see, if y to the power p is an element of x, then if I talk about the cyclic group generated by y to the power p, then it must divide the order of x, hence it must divide q, right? Therefore either it can be p or it can have order q. I mean either y to the power p has order 1 or it has order q. That's what I'm trying to say. Therefore either y to the power p is equals to e, that is the case if it has order 1, else it can have order q. But if it has order q, then observe that y to the power q will come out to be p, since p is not equal to q and both are primes. So in a way they are co-primes, right? Yeah. So this is the Cauchy theorem for finite abelian groups, and hence we have successfully proved the generalized Cauchy theorem. Okay. Okay, there are certain things which I also need to discuss in this lecture, because I want to finish the observations, the important observations in class equation in this very lecture itself. The next thing is also quite important to observe. We want to discuss conjugacy in Sn. Okay, clear? What we essentially want to discuss is that the number of conjugacy classes in Sn is basically the number of conjugacy classes is what I want to talk about. The number of conjugacy classes in Sn is exactly equal to the number of partitions of it. That is what I want to establish. Okay. See, if I talk about any arbitrary partition of Sn, if I am able to decompose it into distinct cycles, disjoint cycles, then obviously I'll get a partition of it. Partition of it. For example, suppose I talk about this partition. We know that every permutation can be represented in a way such that you have a number of disjoint cycles in some sort. So you have, say, sigma is equals to 1, 2, 3, 4, 5, 6, 7, and here you have 3, 2, 4, 6, 1, 5, 7. Then sigma can be written as, so 1 goes to 3, 3 goes to 4, 4 goes to 6, 6 goes to 5, 5 comes back to 1. Yeah, we are done. And then the other numbers we have, 2 is mapped to itself, so we don't want to include it. 3 goes to 4. Yeah, so 3 is already there, right? What is the number of elements left? Yeah, I guess there's no element left. Yeah, this is the only cycle we present here. Yeah, we can do it like 2 and 7. This will enhance the case. So then this is, what is the length of this? This is 5, this is 1, and this is again 1. Observe that 5 plus 1 plus 1 is 7. So, and we are talking about sigma being S7, which is obvious by the way we represented sigma, right? So therefore, if I consider a permutation and I break it into disjoint cycles, then the lengths of each of those cycles will give us a permutation of the number n. Okay. So therefore, if sigma is in Sn and sigma is decomposed into disjoint cycles of lengths, say n1, n2, and so on and so forth till say nk, such that n1 is greater than equals to n2 is greater than equals to n3, and this follows till nk. That is, we are arranging this as say 277 times 1 3 4 6 5, so 115, right? I guess this is time, yeah, such that then then n is equals to n1 plus n2 and so on and so forth till nk. So we get a partition of n. Okay, so we represent such a permutation, which can be decomposed into disjoint cycles of length n1 till nk, such that n1 is greater than equal to n2 is greater than equal to n3 till nk, such that then obviously n will be written as summation of n1 till nk. We represent such a permutation as n1 n2 till nk. This is also one form of writing a cycle decomposition, okay, in terms of its length, which gives a partition of it. Okay, what we want to show is that if I consider two permutations from Sn, then they are conjugates if and only if they have the same cycle decomposition. We claim that two permutations from Sn have the same cycle decomposition, if and only if they have the same they have the same cycle decomposition if and only if they are conjugates. I should have written this in the other way around. That seems more precise. Okay. So Sn, two permutations for Sn are conjugates because we want to emphasize over them being conjugates. Are conjugates if and only if they have the same cycle decomposition. They have the same cycle decompositions. Okay. Now see, if they have the same cycle decomposition, then it's trivially true, right? Because observe that, suppose, let me change the color. Okay. Suppose you have, let's say, sigma is equals to say a1, a2 till say alpha 1, alpha 2 till alpha k, or let's say alpha in 1. Then you have beta 1, beta 2 till say beta n 1 we have written here, right? Let's say beta n 2, and so on and so forth till say x1, x2 till xn r, let's say. Okay, and let's say tau is coming out to be a1, a2 till an1, b1, b2 till bn2, so on and so forth. Let's say here you have y1, y2 till ynr. Okay, clear? Then clearly I can write tau as theta inverse sigma theta, where how should I represent theta? I should just map the corresponding elements. So theta is the permutation which maps alpha 1 to a1. alpha 2 to A2 till alpha n1 to an1. Then I have beta 1 mapped to B1 till beta n2 mapped to bn2, and so on and so forth. I have x1 mapped to y1 and xnr mapped to ynr. Clear? Clear? Okay. This will do the job. Now the converse part is also quite quite easy to observe if you just observe how permutations work or how these functions work. Conversely, conversely, let sigma be in Sn such that, let's say, sigma sends I to j. Okay, sigma sends I to j. Then observe that suppose let's say suppose theta is in Sn such that theta sends I to S and j to T. Then theta inverse sigma theta sends S to T. Okay. An example, let's say an example, suppose sigma is 1 2 3 4, say 2 4 1 3, and let's say theta is equals to 1 2 3 4 4 2 3 1. Okay, arbitrary permutations, let's say. So see sigma, so what is sigma theta? So observe that sigma theta is nothing but, so 1 2 3 4, so 1 goes to 4 here and 4 goes to 3, so 1 goes to 3, then 2 goes to 4, 3 goes to 1, and 4 goes to 2. And then what is theta inverse sigma theta? So it is simply 1 2 3 4. Yeah, so I just multiply theta inverse on the left hand side, right? So 1 goes to 3 here, and then I guess I have 1 goes to 3 itself. Here 1, 3 goes to 4, and 4 goes to 2. Right? Let us check our observation. See, sigma sends 2 to 4, and theta sends 2 to 2 and 4 to 1. But what does theta inverse sigma theta send to? It sends it 2, sent to 1. Right? So 2 is sent to 1. Yeah, that is what I was talking about. Clear? Moreover, observe that. So what observation do we actually get out from here? Is that if I consider an element sigma in Sn and theta in Sn, then theta inverse sigma theta is the cycle, or the permutation is the permutation where we replace every symbol in sigma by its image under theta. So every symbol in sigma is replaced by its image under theta. That's what we are typically doing. Okay, but that immediately means that theta inverse sigma theta and sigma have the same cycle decomposition. Right? Right? I guess it's clear. Okay. Or at least the cycle of sigma and sigma inverse theta inverse sigma theta have the same length. I should talk about theta inverse sigma theta and sigma have the same cycle, same length of cycles. So in fact, the same cycle decomposition as well. Right? I mean, each cycle will conserve its length. Clear? Okay. So two cycles, if are conjugates, then have the same cycle decomposition. And if I start with two permutations which have the same cycle decomposition, then they are also coming out to be conjugates, right? Therefore, what we claimed is lemma, the number of conjugacy classes in Sn is Pn, which is the number of partitions of n. Number of partitions of n. How does it come? Because we have already seen that the cycle decomposition of any permutation in Sn actually constitutes a partition of n. Therefore, the number of conjugacy classes is exactly calculating the number of possible cycle decompositions of the permutations in Sn. And the number of possible cycle decompositions in the permutation is Sn is calculating the number of permutations of n. Hence this lemma. Okay. Clear? Okay. Finally, we will end this lecture with two simple observations of class equation or simple applications of class equations. So let's say applications. Okay. I want to find the number of elements which commute with the 2 cycle 1 2 in Sn. To calculate the number of elements which commute with 1 2 in Sn. Okay. First thing first, all the permutations in Sn which has 1 and 2 fixed will permute with this permutation. Let this be sigma. All tau, or let me say, all tau in Sn such that tau sends 1 to 1 and 2 to 2 will commute with sigma. Because the problem in commuting only comes to when the fact is that both the permutations are having some images of the elements of same elements. That's when the problem in commuting happens. So if I consider all those permutations which has 1 and 2 fixed, then I'll get that element to commute with sigma. What are the number of possible permutations which has 2 of their elements fixed? They are exactly so how many elements should be there? So we have n elements which are getting permuted. 2 of them are fixed. So we are left with only n minus 2 factorial such permutations. Okay. Moreover, see 1 2, or I should say sigma commutes with itself, right? Sigma commutes with itself, and any power of sigma to the power alpha also commutes with itself. Commutes with sigma. But the order of sigma is 2, so the only possibility for this for alpha is 1 or 2. 1 is already checked, and if alpha, sigma to the power 2 will be identity. So identity and sigma are what we are talking about, right? Therefore, the elements which we have yet found to commute with sigma are the elements of the form 1 2 to the power I times tau, where tau fixes 1 and 2, and this is obvious, where so I is 0 or 1. Okay. So how many elements should I get? I get 2 elements from this power, and then I get elements from tau. So I have exactly 2 times n minus 2 factorial elements, right? Okay. Clear? Now, is our observation precise? That is, are these the only elements? That is what we need to check. How can I find the conjugacy class of 1 2? So it is the order of Sn upon the order of the centralizer of 1 2, if you recall, right? Now what are the number of conjugates, distinct conjugates of 1 2? They will precisely be all the transpositions, right? Every element which is a 2 cycle, will be a conjugate of 1 2 because they are having the same cycle decomposition trivially. So therefore, so this must exactly be equal to the number of distinct transpositions. And how do we calculate distinct transposition? So this is exactly having the value n times n minus 1 upon, right? Right. So this gives us the number of distinct conjugates of 1 2. So this implies, suppose I exactly don't know what are the number of centralizers of 1 2. Suppose this is R. So I have n factorial upon R to be equal to n times n minus 1 over 2. Right. This implies R is equals to 2 times, so n comes down, you get cancelled with this n minus 1 times. So you have, right? So n into n minus 1 upon 2 is what you have, and here you have n factorial upon R. So this comes out to be 2 times n minus 2 factorial, right? Clear? Okay. Therefore, these are the only number of elements which we give here, are the elements which will commute with uh, 1 2, the permutation 1. Our observation is precise, right? Because the number of centralizers of 1 2 is precisely coming to be R, which is the number of elements which we are talking about. That's exactly the number of elements which concluded out as well, right? The centralizer is precisely the elements which will commute with n minus 2, which will commute with the cycle 1, right? That's exactly what we are trying to get. So we have actually given the elements which will commute with 1. Getting my point? The next observation is also very similar to this. Here we want to talk about the number of elements which commute with the n cycle. Okay. Consider the n cycle, 1 till n in Sn. We want to find the number of elements which commute with Sn. Trivially, if I consider the order of the, suppose this is sigma, the order of the centralizer of sigma to be u, then again by our class equation, you might say, let's say by class equation, let's say, or by the counting formula, you can also say counting formula. What do we have? We have the order of the distinct conjugacy classes of sigma will be the order of Sn upon u. Now what are the number of distinct, so all the distinct conjugates of sigma will basically be the number of distinct n cycles in sigma. Now if you recall the concept of a circular permutation, we are talking about n cycles, so we have a circular permutation of n elements. There are only n minus 1 factorial distinct circular permutations. In other way, the number of distinct n cycles are of n elements are simply n minus 1 factorial, right? Clear? And order of Sn is n factorial, thus clearly u is n factorial upon n minus 1 factorial, which is equals to n, right? So there must be exactly n elements which will commute with sigma. But observe that we already have in hand that every power of sigma will commute with sigma, and sigma is an n cycle, so its order is n. Therefore we already get the distinct, there exists distinct powers of sigma, which is precisely sigma, sigma squared, sigma cubed till sigma to the power n, which will commute with sigma, including the identity element as well, right? And we are also getting the fact that the only number of possible elements which can commute with sigma is n. Therefore the only elements which commute with sigma are its distinct powers, right? Clear? Okay, so let this lecture be up to this much. In the next lecture we will be talking about the fundamental theorem of finite abelian groups. So meet you guys in the next lecture.